start with some questions. At this point, we've done all of chapter 4. You guys would have finished up your 17 to 23, some story problem worksheet, the review. Should have all been stuff you kind of finished up over break here, or maybe before the start of break or whatever. Or even stuff in the past, like hit me with some questions. We'll go through some stuff, and then we're going to start chapter 5 after that, and get in, get out, get some stuff done in the meantime.
This will be our last test before.
Yeah, I think that'll probably be what it's looking like. Thanks.
You got all I got one.
Yes, sir.
Did you know you had all worksheet 3?
Worksheet 3, number 3.
No, I didn't. No. You said, did you get a haircut? No, I got them all cut. You just get one haircut. No. Oh, you got that cut.
It's a joke between the word hair space cut versus the compound word haircut.
Yeah, no, I get it. Don't worry. I'm on the page. Oh, I'm there. I'm getting it. You're dropping it. I'm picking it up.
Oh.
One for you to flow out.
It's I used it earlier. All right, so Nick had asked about number 3 on worksheet 3, so that's this, right? Okay. So it says you climb onto the roof of your friend's house to scare them when they get home. You find a 25-foot ladder and place the base of the ladder exactly 15 feet away from the house. What is the measure of the angle in degrees that is formed between the ground and the base of the ladder? So that's that. So there's our picture. Nick, we okay with what we did there? Okay. So if I look at this angle, the two sides we know related to that is that opposite, adjacent, or hypotenuse. Okay. And this one is, so the trig function we need is cosine. So I'll say cosine theta equals adjacent over hypotenuse. And then to solve for theta, we'll just do the cosine inverse of both sides. And then it's just calculator time, my homies. So before I do that, I do need to be careful. So I need to make sure my calculator's in the correct mode. Since the answer is being requested in degrees, I want to make sure I'm in degree mode. And then we'll just do cosine inverse of 15 divided by 25. And I got about 53.13. And that'll do her. Sound good? Excellent. Emily, what you got? Sure. Is that another story problem, I think? Methinks. All right. Standing on the street in the middle of Chicago, you look up at a building, and the angle of elevation to the top of the building is 43 degrees. Okay, so I'll just call that position 1, 43 degrees. 200 feet closer to the building, I'll call that position 2. I guess I'll call that T for top and B for base. The angle of elevation is now 58 degrees. And we're asked then to find the height of the building. So far, so good. When I look at this, I see two right triangles. Both of which that involve the angle X. Or I'm sorry, the side X. So far, so good. But I need to know something about a second side in each of those two right triangles that I drew. Well, I know that this much of my triangle is 200, right? So what I'm going to do is I'm just going to call that part of the triangle, or that part of that side, y. So this one would be like 200 plus y, and this one would be like just y. And what I'll do now is I'm going to set up a system of two equations. So from the first triangle, I can say that tan of 43 is equal to opposite over adjacent. And I can say with the second triangle that tan of 58 degrees is equal to opposite over adjacent. And what I'm going to do is I'm going to then solve this system of two equations using substitution. So the way I'm going to do my substitution is I'm going to get each of these equations to equal x and then set them equal to each other. So if I cross multiply this equation, I get that x equals 200 plus y times tan 43. If I do the same thing to this equation, I get x equals y times tan 58. Feel good? Since they're both equal to x, I can then set them equal to each other. And what I have now is one equation that has just one variable in it, y. Now that y is in two different places. So to solve for y, what I'm going to do is I'm going to start by distributing the tan 43. And I'm going to move the y's onto the same side. So I'm going to subtract y tan 43 from both sides. Now that the y's are on the same side of my equation, if I look at the right-hand side, there's a greatest common factor of y on the right-hand side, because each term on the right-hand side contains a y. Everybody see that? So what I'll do is I'll factor out that greatest common factor of y. And what I've done is I've changed that right-hand side from being a subtraction problem, and I've turned it into a multiplication problem, right? So the coefficient on the y is really that tan 58 minus tan 43, whatever that number is. So to get the y by itself, I'll now divide both sides by that tan 58 minus tan 43. And that will get the y by itself. Notice in the previous step, by factoring that greatest common factor of y, I changed the equation from having two y's in different locations to having one y in just a single location. Now that the y is by itself, I'm going to go ahead and type this into my calculator. So alpha y equals, and I'm going to choose option 1. That'll give me the horizontal fraction bar, and that'll let me type this thing in exactly as it looks like on my sheet of paper, so I don't have to muck around with a bunch of parentheses. So typed it in just like the way it looked. So y is about 279.3. I think we were in feet. But that's not what I wanted to solve for, right? I was trying to solve for the height of the building, which was x, right? To get the x, I know that x is equal to y times tan 58. So 279.3 times tan 58. So I'm just going to take my calculator and take my answer and multiply it by tan 58. So I get 446.9. And I'm all dunzos. Emily, does that feel okay there? Okay. I know that's a lot. But it's one of those, like, you do it a couple of times and the pictures all kind of end up being the same. The pattern ends up being kind of all the same. You do 2 or 3 of those and it's like, okay, I kind of get this now. I can sort my way through it. It does take a little bit of practice though. It's a little, the algebra is a little complicated, but the nice part is the procedure is the same, right? What do you guys think? What else do you want to talk about? Probably some worksheet 1 and 2 stuff. What do you guys got for like for that kind of stuff? The same thing as probably the first couple of questions from the review. Want to do one of these guys? You want B? So number 2B, or not 2B, seems like a good question. Some English jokes for you guys. It's Hamlet, my man. All right. So, it's 3B. Ah, that ruins the joke. All right. So, how do we start one of these? I want to start by drawing my picture. And I like to start by first identifying what quadrants are covered on the interval from pi to 2 pi. So, because they're positive, I'm going to count counterclockwise. Hey, look, I started at pi. So that covered quadrants 3 and 4. Then I'm going to notice here, to figure out the second part, cosine is positive, right? So I remember from All Silly Turtles Crawl, cosine is positive in quadrants 1 and 4. So my answer, I know now, has to lie in which quadrant? 4. So there's my theta. Everybody's okay with that? I label that angle between the terminal side and the x-axis. Well, I should say the acute angle between the terminal side and the x-axis is alpha. And now I'm going to write my equation. So I'm going to ask myself, how are the values of theta, alpha, and that side of the x-axis that forms alpha, how are those related? Is theta bigger than 2 pi or smaller than 2 pi? Smaller, because it stops before it gets there, right? Okay. How much smaller than 2 pi is it? It's alpha smaller, right? Everybody's okay with that? And how do we compute alpha? It's going to be, in this problem, cosine inverse of the absolute value of 0.52. And now it's calculator time. So 2 pi minus cosine inverse. Now you're going to see me not type in the absolute value here. Why did I not do it? Because I did in my head, right? Oh, why? What's wrong here? Why did I get a kooky answer? Yes, very good. What mode should my calculator be in for this problem? No, look at the radians, right? Because the angles here were given in radians. And the directions tell me radians, so I have to change it back because I was in degree mode for those story problems. Is that something you're going to have to worry about? Yeah. Yes. Ugh. So about 526. Can I check that? How do I check it? I'll do cosine of that answer. And what should I get when I do that? 0.52. Very good. And then what's the second half of the check? Has to be between pi and 2 pi. Now I can do this part without my calculator because I know pi is 3 point something and 2 pi has to be 6 point something. 5.26 is between those. You could always type in your calculator and get the decimal though, right?
Check it, and it's the same thing as like 2.52, but it's not in between. Does that ever happen?
That could happen. The mistake that is likely made is either you added alpha when you should have subtracted, or you forgot to do the absolute value. Those are the two most common mistakes. If you get one half of the check to work, but the interval fails, it's probably you forgot, you added when you should have subtracted, or you forgot the absolute value. Does that feel okay?
Yep.
Nick?
That one is the theta in like the graph.
No, I just wrote theta because it's like theta is this whole thing, right?
Okay.
So I just wrote it on there somewhere where it wasn't in the way.
And then I don't either you like subtract or add.
So if it was from the picture. Remember we said that theta was smaller than 2 pi because it stopped before it?
Yeah.
How much did it stop before? Well, alpha before. So theta must have been 2 pi minus that alpha, right?
The bottom two columns are always subtract, top two are always add.
No, it would be like these quadrants would be subtracting 2 and 4, and then 1 and 3 would be adding quadrants, assuming that the angle's positive. If the angle's negative, then all that stuff is reversed. I never think about it that way. I always just kind of draw the picture and just like, yeah, that's cool. Totally fine. I'm a picture guy. Like I'm going to spend all this time drawing the picture so I don't have to worry about like memorizing, like what do I do where? It's just like I look at the picture and it's like, oh, that's the relationship. How do you guys feel? Does this bring back, jog memories a little bit? It's like, okay. The one other kind of problem we had were these worksheet 4 problems. Should we do one of these guys? Okay. I'm just going to pick one. Is that okay with you guys? All right. And then I think we've seen like a decent example of like all the stuffs. All right. Any of these look appealing to you? 7. Okie doke. So we always start with the inside, because that's going to be what gives us our angle. What the heck does arc cosecant mean? Arc. What does arc mean when it's in front of those? It's the same as the inverse, right? Everybody's okay there? So I can say cosecant theta then must be 2x plus 1. What is cosecant in terms of opposite, adjacent, hypotenuse? It's sine, it's the reciprocal of sine. So sine is opposite over hypotenuse, but this is the reciprocal, so it should be hypotenuse over opposite, right? And I'm just going to put 2x plus 1 just over 1, so it's a fraction. So what I can say here is that the opposite side should be 1, and the hypotenuse of my triangle should be 2x plus 1. And I'll call that adjacent side then y. What I need to do next is I need to rewrite y in terms of x. So what relates the 3 sides of a right triangle together? Pythagorean theorem. So when I write that, what do I have to remember about the Pythagorean theorem? The hypotenuse has to be the c, right? So I have a squared plus b squared equals c squared. Now how do I do 2x plus 1 quantity squared like that? Not that word. You FOIL it. Because that's 2x plus 1 times 2x plus 1. You said factor. I knew what you meant. So when I FOIL that out, I'm just going to do that in my head. Is that okay with you guys? I get that. So to get the y by itself, we'll subtract 1 from both sides to start. And then we'll square root both sides. But we can drop the plus or minus in this situation because what is y representing? Not an angle, right? It's a side length, right? Can side lengths be negative? No, Mr. Kulik, they cannot. Okay, very good then. So we can say that. And now, if you're feeling fancy, you might notice that, hey, there's a greatest common factor of 4 underneath the square root. And I know that we can break a square root at multiplication. And the square root of 4 is just 2. Now, it's not wrong if you don't do that, but if you're taking like a multiple choice test, like an ACT or something, if you're looking at the answers, surely the answer would have that simplification done to it. Would I mark it wrong without it? No, because it's not technically incorrect if you didn't do that, but we're just talking right now, right? Okay. But the point is now that my triangle is complete. So now I go back to my original problem, and I can do the outside, right? So cotangent is what in terms of opposite, adjacent, and hypotenuse? So, yes. Oh my God, come on, you stupid machine. Yeah, so cotangent is the reciprocal of tangent, which is opposite over adjacent. So cotangent must be adjacent over opposite, right? If I go and I look at my picture, the adjacent side is 2 root x squared plus 1, or plus x, excuse me, and the adjacent side, or the opposite side, is 1. Or you can just call it 2 root x squared plus x. Feel okay? Meh. I think that's about all the skills for this chapter. Yeah.
Could you go like the 4th page on the review?
4th page on the review? Sure. Okay.
Page 4.
Oh, okay.
Can you do like one of those?
Sure. Do you have one in particular you'd like to talk about?
Just a
B? Sure. So we always start on the inside. So tan pi over 3, or I'm sorry, 3 pi over 4. That's a unit circle angle. So I'm going to go to my unit circle. Use that one. So 3 pi over 4 is here. And tangent is y over x. So it's root 2 over 2 divided by negative root 2 over 2. So that's just going to be negative 1, right? Okay. Come back anytime. There we go. So that stuff just becomes negative 1. So I have tan inverse of negative 1. Now, are we given an interval to solve over? No. So we're going to use the range for the tan inverse function, which I remember is negative pi over 2 to positive pi over 2. So if I look at where tangent is equal to negative 1 between negative pi over 2 and positive pi over 2, well, negative pi over 2 to 0 is covering quadrant 4, and 0 to positive pi over 2 is covering quadrant 1. So I'm looking for where y divided by x is negative 1 over here in one of these two quadrants. So I see this right here is the spot I want. So my answer should be 7 pi over 4. But there's a little bit of a problem. What's the little problem with that? It's not inside that interval, right? It's too big. So we have to subtract 2 pi from it. We do that, we get negative pi over 4. And that's now inside of our interval. And we're good.
When I was doing it, what I did is I put my calculator in and inverse, and I put it to degrees. It gave me negative 45.
Mhm.
Just put myself 45 circles.
Yeah, and just turned it into radians? Sure. That's fine. You're doing the same thing.
Okay.
Yep. Because the calculator has this range programmed into it, right? That's what the calculator is going to output, is a number in between those two values automatically for you. The first story problem? Okay, which one is the first story problem? come back.
On the last page.
It's on the last page. Okay. All right, let's come back over here. All right. Okay, so we have this picture here. So we're told that this is like 45 feet. And we want the height of the building. So if I think about it, I have this triangle here. So I'm going to figure out the height of the triangle because the height of the building is going to be 3 more than whatever the height of that triangle is, right? Okay, so if I look, I have relative to this angle, I have opposite and hypotenuse. Opposite and adjacent. Oh my goodness. So I'm going to be using tangent. So to solve for h, I'm going to do cross multiply. Zoop, zoop. And I have 45 times tan 32. And now I know that the height of the building is that number plus 3. And I'm all done. Yeah, I just have to make sure I'm in degree mode on my calculator when I do it, because the angles are in degrees, and it should be good. It should be all set. I'm all done. No biggie, right? We have that little extra add 3 feet, but should be relatively obvious once I drew the picture in the fashion I did why we're adding the 3 feet, right? So about 31 feet tall. All righty. That feels pretty thorough, right? Yes. Let's start some chapter 5 stuff then. I think this will be the last chapter that we talk about. As of this point, my plan would be the chapter 5 stuff would be exam only content. We wouldn't do a test for chapter 5. Would I still have homework from chapter 5? Yes. We still have a homework quiz from chapter 5? Yes. Everybody's okay with that? You gotta be, right? It's like, I guess I don't have an option. All right. So in chapter 5, the goal for chapter 5, the end of chapter 5, would be trying to solve more complex trigonometric equations than what we solved in chapter 4. Right? Chapter 4, we figured out how to solve things like sine theta equals 0.45 or something, right? That was as complicated as we got. In chapter 5, we're going to build out the tools we need to solve more complicated equations, maybe like, sine squared theta plus sine theta equals equals 0 or something. So we're going to learn how to solve more complicated trigonometric equations that may involve more than one trig function, or even different ones, right? Like we might learn how to solve anyways, it doesn't matter. We'll get to it when we get to it. What we want to start, though, is building out some more relationships between sine, cosine, tangent, cosecant, secant, cotangent. We're going to call those relationships, we call those relationships identities. And what do we mean when we say an identity? Well, an identity is just an equality statement, so it has an equal sign in it, that is valid for all values of the given variable. So let's look at some examples of some things that we'd consider identities. Is that an identity? Yeah, right? That's true for all values of x. 2 equals 2, 3 equals 3, 0 equals 0, 1.65 equals 1.65. How about this? Is this an identity? Yeah, how do you know? Sure, that if you just distribute the 2 on the right-hand side, you end up with the same thing as the left-hand side, right? That an identity? Yup. How do you know? You could FOIL out the right-hand side and you'll get the same as the left-hand side. Or alternatively, what else could you have done? Could factor the left-hand side and you'd end up with the same thing as the right-hand side. Now, can you guys think of well, I should say, actually, not can you think of. We've actually discussed several trig identities already. Can you think about a relationship between like sine, cosine, tangent, secant, cosecant, cotangent that we've already used? Let me give you a hint. Yeah. Oh, well, let me give you an example. So there's a relationship between sine and cosecant. What's that relationship? They're reciprocals. So like cosecant theta equals 1 over sine theta, right? And we could do that for each of the 6 trig functions, right? We'd write sine theta equals 1 over cosecant theta, et cetera, et cetera, et cetera. That's going to give us our first set of identities. We call these guys the reciprocal identities. So sine is 1 over cosine, cosine is 1 over secant, tangent is 1 over cotangent, cosecant is 1 over sine, secant is 1 over cosine, cotangent 1 over tangent. We already know these already, right? We've kind of established this early on. You didn't know you learned an identity, our trigonometric identity already, but we knew 6 of them already. That's pretty good. You actually know some more. So remember, when we're using the unit circle, how do we find tan of theta? If I say, give me tan of 45 using the unit circle, what do? You should be able to answer this. Something we've been doing a lot of over the past several chapters. Should feel reasonably comfortable about using the unit circle to do stuff like this. If I want tan of 45, so I locate where 45 degrees is on my unit circle. I find the point at 45 degrees, and I write tangent as y over x, right? And on the unit circle, what does y represent? Sine theta, right? And what does x represent? cosine theta. So can we say tan theta is then, it's just sine theta over cosine theta, right? And if cotangent's the reciprocal of tangent, what can we say cotangent is? Cosine theta over sine theta. Very good. That's our next set of identities. We call those the quotient identities. We also already kind of knew these ones, right? Oops. So far, so good. I'm not doing anything yet. We're just kind of discovering some relationships and kind of making note of them. We'll show you how we're going to use these a little bit later. But first, let's just kind of go and discover some stuff. Okay. The next set of identities we have is if we have some right triangle with angle theta, let's call the sides opposite, adjacent, and hypotenuse. I don't know why I wrote opposite when I said, it's probably because I was saying opposite when I was trying to write hypotenuse. And let's look at what we get if we do sine squared theta plus cosine squared theta. In this right triangle, what is sine of theta going to be? Well, what's SOHCAHTOA say? Opposite over hypotenuse. And cosine is adjacent over hypotenuse. And then how do I square a fraction? If I have like 3/5 squared, how do I do that? Oh my gosh, guys, that's like a 6th grade question. You square them, the top and the bottom. No, that's correct. You square the top and the bottom because like 3/5 squared is like 3/5 times 3/5, and you just multiply across, so you have 3 times 3 over 5 times 5, right? Okay. Everybody's still doing okay? What do you notice about the denominators of these two fractions? They're the same. What does that mean we can do? Add them. So we just add the numerators, but the denominator stays the same, right? What does opposite squared plus adjacent squared have to equal? Remember that opposite and adjacent are sides in a right triangle. Hypotenuse squared. Why? The Pythagorean theorem. Yes, sir. And what is hypotenuse squared over hypotenuse squared have to equal? Oh, it's too much delay here. What's 3 divided by 3? It's hypotenuse squared over hypotenuse squared. There you go. Goodness, great googly moogly. So what do we have here? Sine squared plus cosine squared is equal to 1. We call this a Pythagorean identity. There's actually 3 of these. That's our next set of identities. So far, so good. Again, me deriving them are not things you'd ever have to repeat. I'm just kind of giving you some background so that it doesn't feel like Mr. Kulik just made some stuff up and wrote on a piece of paper and say, okay, use these rules that I just made up. I didn't make up, we discovered them together. The next one, so if we look at the unit circle, oh really? Okay. Let me grab that real quick. Have you ever noticed how like sine of 30, which is 1/2, is the same thing as cosine of 60, also 1/2? And that happens like kind of all the time, right? Or that like sine of 45 equals cosine of 45. Or how like sine of 0 equals cosine of 90. What do you notice about the relationship between those pairs of angles? 30 and 60. 45 and 45, 0 and 90. Think back to geometry.
They're all part of numbers like set triangles.
Well, they are special right triangles, sure, but think more generally than that. Because we'd expect to say that like sine of 13 should equal cosine of like 77. They add up to 90. What do we call those angles? Complementary, right? So that's going to give us our next set of identities. This is actually true for sine and cosine, for tangent, cotangent, and secant and cosecant, that they are equal to the complement of the other. So here we've just written, instead of like, so I'd have like sine of 13 equals cosine of 90 minus 13. Instead of 90 degrees, though, we've written it in radians as pi over 2. But that's the same idea. And our last set of identities is going to come from what we remember about odd and even functions. Remember way back to chapter 1 when we talked about odd and even functions. Does anybody remember what the definition for an even function was? It starts f of negative x equals
Like g of negative x.
good. Well, it'd be f, since we're using f as our function, is f of x. And what's the odd one then? You mean negative f of x, right? Now, if you remember back in chapter 3 then, we talked about when we did the graphing for sine, cosine, and tangent. You remember we said that cosine was an even function, and then sine and tangent were odd functions. If cosine is even, its reciprocal function should also be even. And if sine is odd and tangent are odd, their reciprocal function should also be odd. So what we can say from that is something like sine of negative theta is equal to negative sine theta, since it's an odd function. And we can do that for all of our 6 trigonometric functions, depending if they're odd and even. Now, since cosine is an even one, if I did cosine of negative theta, since it's even, that should just be cosine theta, depending on whether we're talking about an odd or even function, but that's them. So that's our last set of identities, the odd-even identities. Now, Mr. Kulik, the kind and generous man that I am, I've collected all these identities together onto one sheet. So they're all in one place for you. You don't have to hunt through your notes to find them or hunt through the lessons to find them. I've collected them all together into one sheet. Next time you come to class, I'll give you the printout of it. Everybody's okay? That's all we did here in the start of this lesson, was kind of show you how we discovered these identities, right? They give you like the simplest and quickest explanations. Sure, but like, I think it's good enough for you to see that this isn't just made up. Everybody feel convinced? Let's start talking about now how we can use these things to solve trigonometry problems. Okay? So we'll start some examples today, and we'll do some more examples next, or well, not next time, we're taking the test next time, but on Monday of next week, we'll do some more examples from this, so we haven't gotten too far here. Let's look at this example. So this question says, find sine of theta if tan of theta is equal to 3 and cosine is negative. So first thing I want to do is I want to deal with this part of it. Okay? So I know that if cosine is negative, what else can I say is negative? Its reciprocal function also has to be negative, right? If I have negative 4, its reciprocal is negative 1/4, right? It's still negative. So I know secant theta is also got to be negative. Now what I want to do is I want to look for an identity that relates either tangent and cosine only together, or tangent and secant only together. So I'm going to go to my identities and look for one where I have only tangent and cosine or tangent and secant. Nothing up here. Nothing down here. Look. P3, tan squared theta plus 1 equals secant squared theta. That's what I'm going to use. So far, so good. Tangent we know is 3. Square root both sides. And then, because I know secant is negative, that has to be negative square root 10. Everybody okay there? Yes, sir?
Why did you use, like, I understand you use reciprocal, but why did you use instead of cosine?
Because I couldn't find a identity that had tangent and secant only in it.
Oh,
That's why I ended up using secant instead of cosine. And then similarly, if secant is negative square root 10, cosine is negative 1 over square root 10. Everybody's okay with that? Did I get that basically for free, right? Just because it's the reciprocal?
do you have to add that cosine part?
Well, I'm not sure if I'm going to need it or not. That's why I'm going to write it down because it's so easy. So the next step now is I want to look for a trig function that involves sine, tangent, and then either cosine or secant. So I want a trig function that involves 3 of these identities.
For the cosine beta, get the head, the bottom.
You mean the negative sign?
Yeah.
Yeah, you can put the negative sign wherever you want.
No, so you can't have it right.
Oh, well, this isn't a final answer.
Oh.
This is along the way because we want sine theta, right? That's what we're looking for. I'm just writing down some stuff along the way. We'll clean up our final answer to be nice, but I'm not worried about rationalizing answers for something that's not my answer. I can just keep it and we'll go with it until we need to deal with it. You know what I mean? I don't want to make more work for myself than I need to. Okay, so if I go to my identities, the reciprocals are out because they only contain two trig functions. But if I look at my quotient identities, if I look at this first one, I have tan theta equals sine over cosine. That involves 3 of the things that I need to use. I'm going to use that one. Oh, what did we call that one? That was R something. R1. No, not R1. It was quotient 1. Okay. Now I know tangent is 3. How did I know that? It gave it to us in the problem, right? Sine theta, that's what we're looking for. Cosine theta, oh, I'm glad I wrote that down. Everybody's okay? So now we'll just cross multiply. So far, so good. What do I get when I multiply 3 times negative 1 over square root 10 together? How do I multiply 2 fractions together? Nope. Just top to top, bottom to bottom. Cross multiplication is a solving technique, but to multiply fractions is just straight across. So I got that. Now I don't like this as my final answer because that's where I'm ready, right? This is sine theta we're finding now. So here I'll rationalize my denominator, but I didn't want to do that I didn't want to do it before because I wasn't sure if I was going to need to do it. If I ended up using secant, then I would have been rationalizing the other one for nothing. I'm just going to wait till the very end and just make sure I take care of it. Then. Okay. I'm going to stop here because this feels like a good spot. At this point, you guys should be able to do 1 through 6, they're going to be like this example that we just did. That feels like enough for right now. When would that be due? Not Sunday. Because we won't have met to answer questions because we're taking a test next class. So it'll be the following Sunday, right?
2 Sundays.
Yeah, 2 Sundays from now. Everybody's okay with that? Okay. What's due this Sunday? And
Do 17 to 20.
17 through 23, and
Worksheet 4.
I think it's 3 though.
3.
The story problem worksheet, which I think is worksheet 3. Worksheet 4 was the inverse inside of a regular, was the triangle drawing one. But a lot of you guys already did parts of that or all of that in some cases and already turned it in. Some of them, if I had it all there, I recorded it already, I think. If you're just missing one part or another, I probably didn't record anything. So some of you might have noticed you already have a grade for the problem set for this weekend. If it was all there, I just marked it in as I was grading the other one. What do you guys think? Everybody okay? Good enough? So far, so good? Okay.